All right, so as for those sketches that was promised last question, our statement reads, for a bar magnet, make careful sketches of M, B, and H, assuming L is about 2A. Compare with the polarization of the material. Okay, let's review that M is the magnetization, similar to polarization. B is the magnetic field, similar to the electric field. And H is the auxiliary field, or the field in matter, and that's similar to the electric displacement field. All right, so M, magnetization, has to run in the material. This is fairly close to what we saw in P, assuming with the polarization being uniform. Now is where we get tricky. So we have the B field here, which runs both inside and outside. Of course, we see that we run through. We don't have any magnetic dipole or any magnetic monopoles, so the fields do connect. Finally, then, we see what H is. Okay, and H is weird. If you look at the arrows in the material, they're running against it, but then outside, we're circulating back into the material. Okay, so when we see the H, that's all external, right? Because the material inside has some magnetic or magnetization. And what we see is that in the electrostatic case, E is external, and the magnetostatic, H is external. Now, whereas if we're inside matter for the electrostatic case, the field lines go internal and external, but only in the magnetostatic case is the magnetic field both internal and external. I'll write that up in a comparison, but it's pretty cool to see how they compare. Remember that the electric displacement D is equal to epsilon naught E plus the polarization. And for the applied field in the magnetic case, we have H equal 1 over mu naught B minus M. So the plus or minus in the magnetization or polarization makes a difference on what the fields do.